Good afternoon. This talk is about Java language features. It's entitled the Spring 2023 edition. And so the reason is that this talk is continually updated as we make incremental improvements to the Java programming language. And I'll have a slide a little bit later on that shows you how we do that and how that lines up with the 6-month release cadence of the JDK. Much of the work in the JDK goes directly into the main line. We have lots of bug fixes and enhancements going directly into the main line. There are also several large projects off to the side that have been worked on for a number of years. In particular, they are Amber, Valhalla, Panama, and Loom. So I'm not going to cover all of these today. There are some talks that cover some of the materials in the other projects today. But today, in this talk, I'll be focusing on Project Amber. So what does Project Amber do? The goal of Project Amber is to explore and incubate smaller, productivity-oriented Java language features. And so the visibility of Amber is very high. When you're programming Java on a daily basis, what Amber hopes to let you do is make your programming experience more convenient, more comfortable, and quicker and smoother. So there are a bunch of different features in Amber, and here's actually a subset of them. So there's a lot going on here. On the each row is a different feature that Amber has added or is adding, in the process of adding, to the Java programming language. And then across the top, you see the 6-month release cadence of the JDK. Now, each of these language features has gone through a couple rounds of preview. So for instance, switch expressions, text blocks, records, and pattern matching for instance of have all each gone through 2 rounds of preview before finally making it to be standardized in Java 17 or beforehand. Oh, sealed classes as well. That's another important one. So those are already finalized in the programming language and have been released already. There are 2 additional features which I'll be talking mostly about today, which are pattern matching for switch and record patterns. And you can kind of tell that there's a theme going on here. There's pattern matching going on. These features are building on top of each other and on top of previous features that have already been integrated into the language. So pattern matching for switch and record patterns are still in preview. They're both previewing at the same time so that we can get feedback from the preview releases and so that we can co-evolve them. So it turns out that instead of some other features have been largely independent of other features in Amber, these 2 features in particular, their design is fairly closely coupled, and so we are previewing them at the same time so that we can work on them together and adjust them to match with each other. So as of Java 20, they are both still in preview. We hope to bring those to a final release in the near future. Okay, so the 2 preview features, as I mentioned, are record patterns and pattern matching for switch. But as a prerequisite for talking about these, I'm going to be talking a little bit about some previous Amber features that have already been put into the JDK. Okay, so the first one is just earlier forms of pattern matching. We'll do a quick review of that because the current features build on top of these features here. So first, a quick review of pattern matching. Okay, so this was delivered in JDK 16, pattern matching for instance of, and so I'll just go directly to the code here. So when you're writing code in Java, you can do a dynamic type check of a variable and see if it's an instance of something else. And this has been in Java since probably 1.0, and this was the pattern here. The first thing you can do is do an instance of check, and that gives you a conditional, that's the result of that is a conditional expression, which you can test with an if statement. And then if you know, for instance, suppose the static type of O is object, and you ask if O is instance of a string. Well, typically you want to operate on that object as a string. And so the next thing you do is cast it. So you declare another variable, string s equals cast a string of the O reference. And then you can operate on S as a string, for instance, by calling the length method. In pattern management for instance of, this idiom that was repeated over and over and over again is now essentially put into the language. We can declare a local variable that as part of the instance of expression. And so O instance of string S is what we call a type pattern. And so what that does is, if O indeed is an instance of the string class, then that does the downcast and then binds that reference to a new local variable whose static type is string. Now, within the block, we can use the string S as an ordinary string variable. Now, S is only in scope where it is true that O is instance of string. And so outside the if statement, the S variable is not in scope. So you can never get access to S unless it is actually a string. Okay, so this seems really simple, but I'm going to break this down a little bit here. There's lots going on. So there's a little bit of syntax here. In the type pattern, you would say O instance of string S. And so that looks just like a variable declaration because it is. It's introducing a new local variable S into scope at this point. Now, it's also adding some semantics here, which is it's doing a type test. So can O be cast to a string? Well, if so, the cast is done for you under the covers. And the result of that cast is used to initialize the S variable. And this kind of pattern, as we're calling it, can, at least in the current version of Java, can only occur inside of an instance of expression. So there's three things going on here. We have our syntax, semantics, and a particular location where we can employ these syntax and semantics. Let's see, did that work? Okay. All right. So let's put this into use here. So there's an example in the book Effective Java that talks about how to write an equals method. And so here you can see what is fairly typically an equals method. What's interesting about the equals method is that it's required to take a parameter of type object. And so if you want to use something from it, you typically do this instance of followed by a downcast. So the first thing to do is we check for reference equality just to short circuit that and return true. And then we say, OK, if O is null, or if its get class is, if its class is different from the class of this object that we're comparing it to, then we know that it cannot be equal, so we return false. And then we do this thing where since we know that at this point, it's a little confusing. There's no actual instance of here, but we've already compared the class objects. So at this point down towards the bottom of the slide, we know that the classes are the same. Therefore, it is safe to cast O into an instance of a case-insensitive string. And so we store that in a local variable. And then now we can operate on it as a member of this class. And so we get its S field and then call equals ignore case on it. So the example here is how if we have a class that implements a case-insensitive string, you want to find out if it's equal to another thing. And so you have to check if that thing is a case-insensitive string. And if so, then you can extract the data from it and then call the methods like equals ignore case that are particular to the case-insensitive string class. All right, now what can we do to improve this code? So you can sort of see this thing going on here. We rewrite this in a slightly different way to make it a little more fit our pattern. So if we set aside the null checks and things, because the instance of expression implicitly does a null check for us. So we can rewrite this equivalently to follow our pattern of using instance of. So we can say, essentially say, if O is instance of a case-insensitive string, and then we do our inline cast and then call Actually, we don't call a method on it. We access a field of case-insensitive string, and then we call equal ignore case on that. So this is equivalent code, but this is still I mean, this is still kind of this is older code. This is JDK 17 and earlier, because we're still using the regular old instance of, and we're casting, and then we're only casting, because of the way this is set up in the Boolean expression, we are only casting if we know that O is indeed an instance of a case-insensitive string. So what can we do to improve that? Well, this follows our typical pattern of we're doing an instance of check, and then we're doing a cast. So we can use an instance of type pattern to clean that up. And you can see that here, where we say return O instance of case-insensitive string CIS. So there, that type pattern fuses the type test and the binding to the new local variable CIS. Now what's interesting is there's no block here, but CIS is in scope for the rest of the Boolean expression. So what we can do is we can then go on and use it to access the S field and then call equals ignore case on it. Okay, so another item of review that I'm going to go over very quickly is something we also added and finalized in the past, which is records. Okay, so JEP 395 added records. This was also released in JDK 16, so this was finalized already. So what a record does is it's a very common pattern to have a class that just represents some data. And objects are great for encapsulating things. If you want to have operations on that object and to have what goes on inside the object be hidden from the outside world. But sometimes you don't really need that. Sometimes you just want a class to represent a convenient aggregation of data. And so I think everybody's using the same point example. What's a point? Point is an XY value. But before records, if you wanted to have a class that just represented data, you actually had to do quite a bit of work to make it play well with the rest of the Java programming environment. So we look at this class point on the left. It has fields X and Y. There's a constructor that takes parameters and initializes those fields. Then we have accessor methods so that you can get the data out of those fields. And then we have our equals method, which is kind of similar to what I was showing on the previous example. You want to be able to compare this point to some other arbitrary object. So we have to do some null tests and some instance of tests and some downcasts and things like that. And then we need to, now if the thing in fact is another point, then we need to extract data from it and then do the comparison. So that's a lot of work in equals. Hash code is another thing. You need to have a hash code function if you want to be able to store these objects in hash-based collections, and so you have to come up with some computation that combines all the fields somehow. And for the most part, that's arbitrary. If you're combining the data of all the fields, then you just have to come up with some formula that does that. This is a typical one. You know, you can argue about making better hash functions and whatnot, but for certain things, this kind of function is perfectly acceptable, and it will work just fine. But it's something that, again, you have to include something like this, because if you don't, your point or your whatever class you're using won't really work very well in a hash table. And then also, toString is yet another thing. Often you just want some string representation of the internal data of the object. And so you have to include one of those too. So all that code on the left is sort of the minimum bar for just storing a couple int fields. So that's kind of a lot. And so that's what records do for us. On the right-hand side, you can see that entire class on the left is replaced by a single line, record point int x int y. And the record feature of the programming language provides all of those for you. It provides the accessor methods, it provides the fields, it provides the accessor methods, it provides the equals method, hash code, and a toString method. All right, so what can you do with a record? All right, so let's show some examples of how to use it. So you can create a new point by calling its constructor with the right number of arguments. If you don't provide the right number of arguments, that's a compile time error, because there's a constructor that's provided that mirrors the fields that are declared in the record. You can access the fields of the record, or the components of the record, as we call it. So those are methods that have the same name as the fields. So p.x and p.y are the accessor methods. You cannot assign to fields or components of a record. And so what we call a record an immutable, or more precisely, a shallowly immutable class. So the values of a record are established at construction time and cannot be changed thereafter. Okay, what methods are provided? So as we saw earlier, there's a constructor that takes two values. There's an equals method that's provided for you that compares every field of the other record. There's a hash code method that's provided, and this lets you store them in hash data structures, such as a hash map. And there's a toString method that does something fairly obvious with the fields, turns them into a string representation, and returns the result. Okay, now let's move on to the preview features that we're continuing to work on in JDK 20. Pattern matching for switch and record patterns. So after that review, these new features build directly on top of those earlier features. Okay, so earlier we talked about patterns that were introduced as part of instance of. So here, what pattern matching for switch is taking that same concept of pattern matching and making it possible to use that inside of a switch statement or a switch expression. And so in those older constructs, you gave a value to switch over, and then case labels or case arms of the switch statement or switch expression had to be constants. And so now we're saying, let's introduce the possibility of using a pattern instead of a constant. So let's say we have an object O, and we want to switch over it. We can say case string S. Now that looks exactly like the pattern that we introduced for instance of. And so what that means is it's the same thing. If O is an instance of string, then the downcast is done under the covers, and the variable S is bound to the result of that cast. And therefore, we can call string methods like length on that S variable. And if O is not an instance of the string, then this case arm will not be evaluated. Okay, now there's something going on here, because you also might recall that the earlier versions of switch statements and expressions had a restricted set of things that you could use as what's called the selector expression. In this case, it's O. It used to be that you could use only integral values, enum, and string. Anything else was rejected. So now you can, basically what we've done is we've lifted the restriction, so you can still use the integral values, or integral types, but you can now switch over any reference type. So you can put an object in there in order to be able to do type tests on that object. Okay, now, but there's something different here, because in the past, when the case arms were constants, they were all independent. And so you didn't have to worry about it, because there was no overlap at all between the different constants in the case arms. But now that we can put type patterns into the case arms, there's this question of order that comes up, and or it might come up. So for instance, let's look at this first code fragment. Again, let's say O has a static type of object, and we want to see whether it's a string or an integer. And so we can write case string S and have it do something if O is a string, and we can say case integer I and have the code do something different if O is actually an integer. Okay, that's fine. Those are independent, and there's no overlap or conflict at all between those two different cases. Now let's look at the second example. Case string S and case char sequence CS. Now you have to know the libraries a little bit, but it turns out that char sequence is an interface and string implements the char sequence interface. So what happens here? Well, it turns out there's a complication, which is that one of these cases is a subset of the other. And so which should we do? Should we do both? Or which one gets chosen? And so there's a design process that the languages team went through to do some evaluation on this. Something that some other languages do is they look at all the cases and they say, which is the best match? And that's one way to do it. That's a very precise way to do it, and it's useful. But it also has an odd wrinkle, which is that if you have a whole bunch of cases, the compiler will look over, or the language will look over all of the cases and find the best one. But if you insert something down here at the bottom, it can change the entire equation. And so there's a slight bit of non-local side effects going on here. Whereas if you change one part of the code, it might have an effect on another part of the code. And so the Amber design team decided that the case arms should be considered in order. So let's look at these again. So if we look at the second example, we say case string s. OK, so if it's a string, then that arm will be executed. And then after that is case char sequence cs. OK, there are objects that are char sequences that are not strings. So that will catch a different set of objects than the string case will catch. OK, that sounds reasonable. Now let's look at the third example. Let's consider these in order. Suppose O is some char sequence. OK, so case char sequence CS. That covers everything, including strings. But then what happens if the case string is down below? Well, that kind of doesn't make any sense now. Should that be caught by the one above? If so, then that means this is dead code. And so that's kind of like in other parts of the programming language. If you write a statement in a method that is not reachable, that's considered a compile time error. So we decided that that should be a compile time error too. So order is significant. So here's what's going on. So in this case, the case string s is not reachable. And the reason is that something above it is a superset and catches every possible case. And so nothing can ever get down to case string s. And so when this happens, we say that the char sequence type pattern dominates the string type pattern. And so if you have something that dominates something below it, then that's considered a compile time error. Because maybe you need, what's telling you is you need to think about this a little bit more. So if cases are evaluated top to bottom, if you have a situation like this, then this is considered an error, probably because it's a programming error. The compiler will tell you about this. So if you really want to handle strings one way and handle other char sequences another way, you just move the string case up above the char sequence case. You can also mix in constants here. So a constant is a pattern, but it just matches a specific value in a pattern. So if we want to special case the word hello, we can say case hello and have it do something. And then for every other string, we can just have that handled separately. And so this works just fine. But again, if you switch the order of these, then string will dominate the constant hello. So you can't have hello occur below the case string. And that's what happens, right? Because string dominates the hello constant. And so this is considered an error. OK, so another limitation of the previous versions of switch, disallowed null. Again, the integral primitives, of course, could not be null. But string and enum are reference types. And in the older versions of switch, if those were null, switch would throw a null pointer exception. And so sometimes you really want to take a reference and do some null testing. And so in the earlier versions of switch, you had to write an if statement outside and deal with it. But here, since we're integrating it with pattern matching, it's an opportunity to revisit null handling and see if we can improve that. So the way we decided to do that was to allow adding a specific case for null somewhere in the switch statement. I mean, it's fair enough. So if you want to handle null, then just put in a case null. Now there's this idea of exhaustiveness. So this particularly comes up when you're using a switch expression. So an expression in Java always must evaluate to some value. Now in a switch statement, you could have several case arms, and if none of them matched, then the statement would just fall through and continue with the following statements. You can't do that with an expression. So there's an extra wrinkle going on with switch expressions, which is that the case arms that comprise that switch must be exhaustive. And that means that every possible value that comes in as the selector must be handled by one of the cases. So if we have this here, if we have any object O, we say case string, oh, do something, case integer, do something else. Well, now what happens? What if it's neither a string nor an integer? Okay, the expression needs to provide a value, and that type of being other than a string or integer is not handled here. So this is considered a compile time error. A switch expression must be exhaustive. So how do you make something exhaustive? Okay, well, it's pretty easy. Just add a default case. Okay, so now it's exhaustive, and so this works just fine. Now, revisiting the switch statement. I said earlier, in the earlier versions of the switch statement, the cases did not need to be exhaustive. And that's something we cannot change at this point because there's too much code out there that relies on the fact that it's possible to write a switch statement and have it match none of the cases and fall through, or fall off the end. And that's okay. That code needs to continue working. However, it's a common source of errors, right? So if you're writing a switch statement and you forget, or if you forget something, or if you in one part of the code you add the possibility of passing in a new value, but you forget to update the switch statement, then that introduces a bug there. So sometimes you really do want even a switch statement to be exhaustive. And so what we're doing is we're saying, okay, if you are using type patterns in switch, even a switch statement must be exhaustive, in addition to the switch expressions, which always must be exhaustive. So that's a way we're making the language a little more bulletproof. Now, what if you wanted a switch statement and you wanted to fall through if object, for instance, is not a string or an integer? Well, just write a default value in. That way you're explicitly saying, okay, I am handling this particular case by ignoring it. So that's manifest in the code, and we believe that will prevent a certain class of errors in using the switch statement. Okay, so this brings in another of the previous Amber features that I mentioned earlier, called sealed classes. And sealed classes play into the exhaustiveness story. So here, in this example, we have a sealed class shape, which is abstract, and it permits three subclasses: circle, rectangle, and square. And you can see the circle, rectangle, and square classes right there. Now let's just think about this very simple class hierarchy for a moment. If you have an object, or if you have a variable of reference type whose type is shape, what can it be? Okay, well, it can be null, or it can be, it can't be a shape because shape is abstract. And what sealed class says is that these classes listed in the permits clause are the only ones possible. So you can't have some code elsewhere that says class quadrilateral implements shape or extends shape. That can't exist. That will not be permitted because there's a permits clause that says only these three can be permitted here. So, so what does this buy us? Well, so if we are switching over some object of type shape, then when it gets into the switch statement, we can have cases for circle, rectangle, and square. And and we're done. Because we know that those are the only possible cases for an instance of a shape. So we don't need to put a default clause in there in order to make this switch be exhaustive. Okay, there's some other things that we've added to switch expressions, switch statements and expressions here. But basically, it's an adjoint to the pattern switch, which is sometimes what you want to do is you want to do a type switch on. You want to do a switch on the type of the object, and then you want to do some additional things like checking the values, right? So we have some arbitrary object O. If it's an integer, okay, great. We know it's an integer, but if it's negative, we want to do one thing. If it's 0 or if it's positive, we want to do something else. And so what happens quite often is that you have a case, and then inside the case you have some if statements. And so really, it might be nice to break those out into kind of the same level as the switch statement. So we can say case integer I when I is less than 0. And so that's sort of integrating a Boolean expression that we're calling a guard clause into the case arm itself. And then you can have several of those. So if we want to have a negative, something that handles it negative, something that handles when I is 0, and then the rest of them are caught if we just have an unguarded case integer I as the third case arm there. So now we're handling not only the cases where O is an integer, but different kinds of values for what that integer is using the when clauses. Okay, now moving on to the next feature that we are previewing in JDK20, which is called record patterns. And so you can see these are all building on each other. We've talked about patterns several times, and we talked about records a couple times. Now we're combining them, and so you can do record patterns. And so the salient point of a record pattern is not only can you do a type test, but once you've established that an object is of a particular record type, the language knows what fields there are in the record. And so you can pull those out and bind them directly to variables at the point where you're doing the pattern matching. And so you can do that both for switch and for instance of. So let's create our point, new point 34. And so now we can say, if e instance of point X and Y. So this is interesting. We sort of are adding arguments to our pattern matching syntax here. And we can do the same thing with the switch statement. So instead of just saying case point P and then do something, we can say case point int X int Y. And so what that does is instead of just binding P to a variable, what it does, it breaks open the records and say, okay, we know that a point has an X and a Y, and so let's take those values and bind them to new local variables right here and introduce those variables into the scope from this point onwards. All right, so let's show this in action. So this is a somewhat involved example. I'll take a little time to go through this. Okay, so we have our record, our point record. We have a color. And we're introducing a new record, a colored point, which is a point combined with a color. Pretty simple. Now, suppose we have a task where we want to say, let's print out the horizontal position and the color of some object that might or might not be a colored point. Okay, so prior to these new preview features, how would you do this? Okay, so we have our object O. We say, okay, so if O is instance of a colored point, we do our typical thing. Now that we know that it's an instance of a colored point, we do our downcast and store that variable in a new CP local variable. And again, we want to get the X component of the point contained within it. So what we have to do is pull out the point from the colored point. So we call cp.p to get the point. But we have to null check it there, because in case it's null. And so if it's null, we'll just return. So let's set aside what to do about that case, because we really do not want to call any methods on a null reference. Now that we have a point in P, and we know it's not null, now we can call the X accessor method on it to get the X value out of it. So now we can, oh, and there's something missing on the slide, actually. So we need to we have the X value, but when we print out the color, we need to call cp.c to get the color value there. Okay, so we can see a bunch of things going on here. We do some instance of checking, we do some downcast checking, and then we do some extraction in addition to downcasting the variable that we verified was the right instance. Okay, so what can we do to improve this code? So one thing we can do is we can turn it into a switch pattern. So we can say switch O case colored point CP. Okay, so that gets rid of some of the instance of downcast stuff. And then now that we have a colored point, then we have another instance of here. So if cp.p instance of point p, so we're doing kind of a nested instance of pattern here. So we're we're downcasting we're probably pretty sure that if it's non-null, it's an instance of point. But what instance of does is it also does the null check. So inside of this inner if statement, we know that p is a non-null reference to an actual point. Okay, good. So now we can call p.x and cp.c to extract our horizontal location and color. Okay, so that's good. But we can do a little bit better. So notice here that we're doing an instance of check followed by a call to an accessor. So how can we combine those? We're using this new record pattern syntax to extract the components of the point record and bind them directly to local variables. So we're saying if cp.p instance of point int x int y. And so now we have x and y variables, and we can just use them directly. We don't have to get a kind of an intermediate variable that stores the point and then call methods on it to extract it. And then we just use x where we want to when we're printing out the horizontal location. Okay, but again, we can apply this this idiom again. Case colored point CP. All right, so now that's just a type test, but we can do an extraction because what do we do with the CP variable? Well, we call an accessor to get the point, and we call another accessor to get the color. So we can combine those into another record pattern. So we can say case colored point, point P color C. And so that extracts the point and the color components from the colored point into local variables, and then we can just use those variables directly. But notice again that we still have some things going on here. We've extracted the point from the colored point, but then we turn around and do an instance of to extract things out of that. And so we can actually nest patterns. And so we can take that point int x int y pattern and nest it inside of the colored point pattern. So now we say case colored point that contains a point int x int y and a color c. And so now we've taken a nested structure and extracted a bunch of things and bound those values directly to local variables without having to do multiple steps of open up something, look at it, oh, is this an instance of something else, look at it, pull things out. So we're doing all of that in one switch pattern here, one record pattern that combines the instance of check, it combines the downcast, and it also combines that with the extraction of values of record components. And then, now that we have x, y, and c, we can just use them inside of this block, and it works just fine. All right, so that's what we're working on for JDK 20. Those are currently in preview. There's actually a whole bunch of other stuff going on in Project Amber as well, and I don't have time to cover all of these, but you can look on the OpenJDK site and see what's going on with them. There's string templates where we can interpolate string values inside of a string. There's what we're calling the on-ramp, which is a way for students and beginners to learn Java more easily without having to deal with boilerplate code. Unnamed patterns, that's something that's also being worked on. So you saw a couple examples there where we wanted to find the horizontal location of a point. So we said point x, y. Well, if we don't need the y location, then why do we have to have a variable for it? So we're coming up with a syntax for saying, OK, extract something, but I actually don't care about this particular value. So the proposed syntax for that is to use an underscore. There's some things about using instance of for primitive values. So currently, instance of works only on reference types. But sometimes it's useful to do the downcast stuff for a wider primitive into a narrow primitive. Sometimes you have an int that you know is within range. And so if you say instance of byte, then you don't want to have to do some fancy masking and checking in order to make sure that the cast you're eventually going to do is safe. Also, we're thinking about ways to use patterns in more places. So right now, patterns can be used in instance of and in switch. And so we're considering to have a statement that can invoke a pattern match somehow. And so the draft for this uses a new keyword called match. It's probably going to turn into something else, but that's what the team is working on right now. And then another area of where a lot of investigation is being done is with pattern matching and extraction of regular classes, not just records. And so this is going to be a lot of work, but it's going to be extremely valuable. So the thing about records is that you're telling the language exactly what components are in it. And so the language can do the extraction of those components. But you might want to have your own class and say, hey, I want to make my class available to the pattern matching construct, and I'm going to provide these values. And so there's a whole bunch of work that needs to be done, but that's something that's being worked on as time goes on. All right, so Project Amber is doing a lot of different things, a lot of different features, some of them independent and some of them dependent, like these whole series of pattern matching features. The idea is to make developers more productive, so there's less noisy boilerplate code to write, less error-prone code to write. There are lots of things going on all at the same time. Because of the 6-month release cadence, the platform is moving very fast. So every release, there's new features or new variation of an old feature that's been in preview. And so we're making continuous improvements every release to the JDK. All of this stuff is public. Go to the OpenJDK website. There's mails to the mailing list. You can read the JEPs. There are early access builds for things. Try them out, write programs, tell us what works, tell us what doesn't work. JDK 20 is available today, and you can download it from here. Thank you.